Welcome to my presentation. Today I will talk a little bit about file system security. My name is Richard. I'm co-founder of Sigma Star GmbH, a small contracting company. Upstream, I am mainly involved in Linux stuff and focus a lot on kernel, low-level components, virtualization, and security. And today I will talk a little bit more about security issues. So, first of all, a short overview. I just have to configure Zoom again, it's in my way. How can I get rid of this toolbar? No idea. Anyway, the goal of this talk is give you an overview of what you can do with file system security on embedded Linux systems. And hopefully this will give you a guidance for a next project that you can look up what you can use next time and how can you use it correctly. And of course, this talk is by means no complete guide how to implement something or implement a whole security config. It's more a collection of pointers and hopefully gives you some new ideas. And then, like I said, pointers to in-depth documentation. So first, let's talk about the motivation about file system security. So this is not completely seriously meant, but this is an overview of some motivations I see more often than I want to. Of course, the best motivation is when you care about customer data on your device and when you care about data integrity. But sadly, it happens a lot that people want to have file system security just to keep their magic source secret, or they have creative licensing on their devices, or just to pass some kind of certification. They just need to get the check mark, okay, the device is encrypted, pass. And they don't care about the details, they just want to have it encrypted. So, but now let's get serious. Before we can talk about some security mechanisms, one of the most important things is you really need to know your threat model. And I will say this not only once in this talk, you really have to know what is the thing you want to protect yourself from. And if you know that, then you can think about what mechanism is the right thing for you and how much are you able to invest. So the first question is, has the attacker access to the hardware? And if so, to a running device, is he able to dump memory? So depending on the answers, you can select different types of mechanism how to protect yourself from. For example, a common question is, has the attacker access to my main memory? Then you have to distinguish, can he do just a cold boot attack by getting the snapshot of your RAM, or can he monitor all your RAM in real time? So just sniffing the memory bus. This is something different, and the latter makes it really hard to get a protection. Also, has he access to a shell? Can he get a root shell? Do you still want the protection when he can take over your kernel? So as an example, when the device is hacked over the internet and the attacker can exploit your kernel, and then he can also inject his own kernel modules, is he still unable to recover some encryption keys? Is this something you have to care about? And also, who is the attacker? Is it just a nosy neighbor? Is this a market competitor? Or is this a state agency? Depending on the mechanism, you have to think, okay, to keep the nosy neighbor away, I have just a little protection that keeps him away for 2 days, and then he will give up. The market competitor maybe will give up after 10 days or 1 month, and the state agency has thousands of hours, and they have much more resources, and they can do much more, and they have the money, the power. So what is the attacker? And who want to get rid of? These are the main questions you always have to ask yourself when you embed some kind of security mechanism. So let's talk also about file system encryption itself. When you talk with some people about file system encryption, everyone means something differently. So for some, file system encryption means encrypting the whole disk at disk level. For others, it means now it's on file system level, but also the file system structures. Some think no, it's just a set of selected files. For others, it's scoped on the directory level. Or others are surprised when the file content is encrypted, but not the file names, or even out of band data like extended attributes. And depending on the mechanism, some of these questions are true and others are false. So you always have to know what you want to have protected and what the mechanism itself will give you. Now, a quick overview about the typical file system encryption methods Linux supports, and you will find on current systems. The first one is Ecryptfs. Ecryptfs is rather old. It's a stacked kernel mode file system, so that means it's not fused, so not in user space, it's in kernel, and it basically encrypts file content and file names on top of another file system. So the main takeaway is that it works on top of an existing file system. It's just a layer on top of that, and it works on a directory basis. So you basically have a folder on your regular X partition, and then you define, okay, let's mount Ecryptfs on this folder, and then the content of this folder will get encrypted. And when you look into this folder without Ecryptfs, you will find file names that consist of garbage, and when you read the file, you will also see just garbage content. One important thing is it's just encryption, no authentication. It cannot protect you from changes. So an attacker can still change your data without getting access to the plain text. There are some problems with Ecryptfs. One is there's a performance overhead from stacking. Usually this is not a big deal on a regular system, but on a memory constrained embedded system, there is an overhead and it's there. But the biggest one is that there's a limit on the file name length. So when you create a very long file name on Ecryptfs, there's a good chance that the file create system call will just fail. So on Ecryptfs, the maximum file length is about 150 characters, whereas on a typical Linux file system, the length is 255. Of course, there's a system call where you can query the maximum possible length. It's part of statfs, but hand to the chest, who of you actually checks this system call before creating a file? You just assume that the file length is good enough and it will just work. So a prominent example of very long files is the Yocto state cache. It creates really long file names, and it happened more than once that I have one guy in a workshop. When we try Yocto, then he is facing very strange build errors, and then it turned out he is using an Ecryptfs home directory with file name encryption, and this explains why it fails so badly. So the reason for this file name limitation is that on Linux, a file name must not contain a null byte or a slash. But when you encrypt a string, the output is no longer a string, it's just binary, and it of course can then contain null bytes or slashes. So That's why Ecryptfs has to encode the ciphertext, so in something like base 64, but this will increase also the length. And this explains why Ecryptfs has this file length limitation, and there's no way to get this fixed. So when you have no problem with shorter file names, easy. But if you need really long file names, then you have to disable the file name encryption of Ecryptfs. So since this talk is on Yocto, how do I use Ecryptfs with Yocto? Yeah, that's actually easy. You can add the Ecryptfs utils recipe to your project. So then you have the Ecryptfs utils package in your rootfs. This will give you a mount command. You have to enable Ecryptfs in the kernel config, and that's it. So before you use Ecryptfs, you have to mount it, and this depends then on your security configuration where you need it. So when you encrypt the whole root file system, then you have, of course, mounted in the Dmcrypt. When you have an encrypted home directory, then you can use PAMs, for example, with the PAM mount module, or even when you use it on application level, then the application itself has to mount its working directory with Ecryptfs to access to the encrypted files. But let's skip to the next encryption method, namely Dmcrypt. Dmcrypt is very commonly used on Linux. It's an encryption actually not on a file system level, it's the layer below on the block layer. It's a device map module. It works with any block-based file system, so that means it does not work with file systems on MTD, namely Ubifs or JFFs2. But these days, block devices are more common than raw NAND. You use it mostly for full disk encryption. It has a rich cipher suite with different modes, but also, like Ecryptfs, it does not authenticate your data. So an attacker is still able to change data without that you can notice it. Again, how to use it in Yocto: you add Crypt setup tool, you enable Dmcrypt, and before you mount the file system on top of Dmcrypt, you have to configure it. Usually this is done in the initial RAMFS because you apply it to the whole file system, and when you use it in your rootfs, you have to do it in the init RAMFS. If you use it on another file system like your home directory, if it is a separate file system, then you can also load it later. But usually you have it in the init RAMFS. That's much more simple. So now let's move over to a system that's not so much known. That's Fscrypt. It's file encryption on file system level, but not stacking like Ecryptfs. It's really implemented in the actual file system. So it's currently supported by X4, F2FS, and Ubifs. That means the file system itself is just implementing the Fscrypt subsystem, but it has to take care itself how to store the encrypted content. And this makes it fast because then it can get rid of all the stacking. It can encrypt the file names and the file content, but the interesting thing is it does not encrypt metadata or the out-of-band data. So especially the out-of-band data is a little strange because many applications store information in the extended attributes, and these are not encrypted. You have a so-called policy per directory. So per directory, you specify an encryption policy. So you can say, I want it for the whole file system. Then you apply the policy to the top, or you just apply it to a subfolder. It has per policy a master key, and for each inode, that means for each file, it's deriving from this master key a new AES key. But again, it has no authentication, it's just encryption. So the primary use case was Android. So Google developed it for Android to have the user's home directory encrypted. But as I said, you can also use it to encrypt the whole file system, and that's why we have support for it in Ubifs, because Ubifs cannot use Dmcrypt, and always using Ecryptfs on UBI is also not so nice because of the overhead. And so we decided a few years ago to implement it there, and commonly on Ubifs you use it for the whole root file system. The main mode of operation is that you mount the file system and then provide a master key using the key control command. And every time a process tries to access a file, the key is grabbed from the key ring, and when the key is available, you can get access to the file, and otherwise the file access will be blocked. That also means that you don't have access to the ciphertext, like on Ecryptfs. When you don't have the key, the file system completely refuses access. As I said before, that Fscrypt has also encrypted file names, but it has not the problem like Ecryptfs. So quiz question, why doesn't it suffer from the same problem with the file names? So the answer is it doesn't suffer because the file name is not stored as regular file name on top of the file system. It's stored internally, and internally the file system can do whatever it wants. And that means internally it's also allowed to have an null byte and a slash in the ciphertext. But there are also some pitfalls. Like I said before, when you access a file, the process in charge, or the user in charge, has to access to the key material. So and when you use PAM key init and you used encryption policy for the whole root FS, then it can happen that upon user login, PAM key init is creating for you a completely new key ring and is removing all the old ones, and then you can end up with a user login session where you don't have any key material and cannot open new files. That's a little bit of a drawback. So usually on systems where I use Fscrypt for the whole file system, I disable PAM key init. There's also a similar problem with systemd, I think, because systemd these days is also touching your key ring. So when you face strange errors after logging via SSH, use key control and check whether the key ring is still present or not. And there's also another, let's say, interesting property, namely the page cache. So when you access on Linux a file, the content is in a page cache. And I said before, when you try to access a file as user A and don't have the key, then you cannot read the file. But let's think about another way. When user A has the key and reads the file, and then later B tries to read it also, but does not have the key, it can still see the content because the content is in the page cache. And the only way to get rid of this problem is you have proper access control using discretionary access controls or access control lists, or for example, you have mount namespace. That means when you have a encryption policy for your home directory, then make sure that upon login you create a new mount namespace, and then that the whole new mount is not even visible to other users. And another pitfall is when you cannot read the ciphertext without the key, then it's also not possible to take backups. So, for example, when you have multiple users on your system and every user has its own key, the root user can only take backups when he has the key. Otherwise, also root cannot read the content. But root can delete files that are encrypted without the key. This is also an use case from Android, so that you can delete some user profile, you lost the password. So again, how to use it? Actually, to use Fscrypt, you just need very little tooling. It's just a thing about a few I/O controls, and there's this Fscrypt control tool. It's written in C. It's a small package. You can add it to a root FS, enable the FS encryption config in kernel, and here's the interesting property. You have to first mount the file system and then later install the keys. So it's perfectly fine to mount the file system without having keys. You need the keys only later when you try to access files. So mounting will not fail if you have no key material. This is also something that can be confusing, because when you have a bug in your key setup and mount and the application starts reading, the application will just see strange file names and all the open system calls will fail. So now let's talk a little bit more about encryption itself. Actually, disk encryption is the last resort option. So when you don't really know what's going on and what to protect, you can always encrypt the whole disk. But actually, you want it for more fine-grained. So you want it in bare directory or in multiple levels. So ask yourself, do you really want to have encrypted something like USR or library? The content in there is already known, so why protecting it? It's much more important that you protect the sensible data, and you can actually also combine it. So encrypt the whole disk using Dmcrypt, but have bare directory encryption for the home directories or the state directories. So have multiple layers. Of course, it comes also with a cost. When you have multiple encryptions, you have double decrypt and double encrypt. But it depends a little on your use case. So I said before that these methods don't protect you from changed content. So an attacker can always change the ciphertext. So when they change the ciphertext and decrypt it with the right key, it will just decrypt to garbage. But a sophisticated attacker can still do evil things. So the most simple thing you can think about is swapping whole files. So when the attacker knows where the encrypted version of, for example, the true program is located, and when he knows where the login program is located, then he can actually change the content of the blocks. He doesn't know what's in the blocks, but he knows, okay, this must be the login tool, or this must be the true tool, and then he can swap it. And then doing login via SSH, then there's no longer the login program used, but the true program, and the attacker can gain access. Of course, this is a much more simplified example. I have in my last slide a link to a paper where they actually show a real attack on the Dmcrypt, where they did such an attack. So this is really possible. And this is also why I'm not really a fan of pre-generated FSM images, because when the attacker gets access to one of these images, he knows the default location of certain tools. And tools like true or login, they don't change a lot. What a lot changes is log files or state directory, but not the programs. And when the attacker knows where the stuff is, he can do nasty things. But there's some help. There are some mechanisms in the device mapper that can help you to detect such changes. The first and simplest one is Dmcrypt. It's a read-only device mapper target, so it works like Dmcrypt, but instead of encryption, it's a layer in between that makes sure that the content is not changed. So the typical use case, you use it for a read-only block device like SquashFS or AeroFS. It's fast. It's using a hash tree. The tooling is part of Crypt setup. the specific tool is called Verity Setup, and enabling is done via the kernel Dmverity option. You can also combine it with Dmcrypt encryption. But only read-only is not so nice, because there's also another one. It's called DM integrity. That's actually the same, or more like the same, like DM Verity, but it supports also writing. So it's basically adding an authentication tag to every block. It can be combined with Dmcrypt, and with this you can have a fully encrypted block device that's also fully authenticated. So that means the attacker cannot see any content, and any kind of change will be detected. But it has a certain overhead. The overhead is in space and CPU time. CPU time is because beside of decrypting and encrypting, it has also make sure that there is a valid authentication tag, and the tag itself needs also more space. So currently DM integrity has two modes how to store these tags. One is a bitmap and one is a journal. So it's really a non-trivial piece of software, and the overhead is really not huge, but you can measure it. So when you have a small embedded system, I would do benchmarks before using it. And like Fscrypt, there's also a mechanism that's called Fsverity that works on file system level. It's supported in X4, F2FS, and ButterFS. You can have integrity checks for single files, but the downside is this single file will then turn read-only. The use case is also from Android. They wanted to protect certain factory reset images or app packages that an attacker cannot change them. So I'm not really a huge fan of it because I don't have a use case, but I thought maybe you have a use case. That's why I make a slide on it. Again, how to use it in Yocto: you install the Fsverity utils package and enable Verity kernel option. Then you can select for single files which should be protected. Then let's talk a little bit about Ubifs, because Ubifs has a unique feature that no other file system in Linux has today. It has full authentication support and is read and write, and supports reading and writing. That means the whole Ubifs file content and file structures are protected. This sounds like a whole lot of work. It wasn't not that much work, because since Ubifs works on raw NAND, it's strictly copy on write, and then you can add basically to each file operation an identification tag, and you get a lot of features for free. But to be honest, the feature is rather new. Oh, sorry, there's a typo in my slide. Its feature is rather new, so it's actually already 3 years old, but embedded folks are slow, so there can be some bugs, and as soon as it has more users, then the bugs will hopefully get sorted out. So I see I have to little be faster. So now you may wonder, hey, what's about generating images? When I use Yocto, then I generate an image. I have my Ecryptfs, and it will give me an image for my SD card and so on. When you use the Dmcrypt and other these mechanisms, this is no longer possible, because there's not much tooling to create such an image offline. And I also don't recommend it. As I said before, a pre-computed image helps the attacker. What I like much more is the installer approach. You create with Yocto just a tarball of the root FS and generate an installer, and then this installer will do all the key setup and lockdown of the device, and then install the tarball. But it depends how you flash later your targets. I did already some some toolings for Dmcrypt to have an image offline, but it's a lot of work and I don't recommend it. So yeah, I will skip over these slides. This just to show you how to create an encrypted FS with the Ecryptfs Ubifs tool, because this tool actually supports this. Same for the identification. So let's give me 2 more minutes for the keys to success. This is one of the major challenges. When you start your fully encrypted laptop, you have to type in your password. And of course, this is not what you want on an embedded system. You don't want human interaction. You want to have that the device just works, but have everything encrypted and authenticated. But this means the key material has to be stored on the device itself to unlock the device. But the attacker must not extract the key. You see the problem. Without hardware support, you can give up there. So you have to have some way to store the key in a secure way. Beware, it happens more often than I want to that people just derive a key from hardware properties. They have some more or less secret algorithm that will take your CPU identifier or MAC address and then generate the key. And as long as you don't know the properties and the algorithm, you're fine, but that's security by obscurity. Please don't do this. Yeah, often you have some secure element, like a DBM chip. It's externally, it can store your key material in a secure way. You can do also encryption on it, but it's slow. So when you do encryption on a DBM chip, it's really slow. So you have to transfer the key to your main memory. But the problem is the attacker can sniff the wires between your CPU and the DBM chip, and he can do the key extraction. The common attack is BitLocker DBM sniffing on Windows. I have a link on my last slide to a tutorial how to do this. That's also why is the reason why enterprise setups also enable the BitLocker PIN mode, that the user has to enter also a PIN code when the laptop starts. There are also internal secure elements. This is when it's part of your system on-chip. A prominent example is the CAM engine of the i.MX CPUs. Here the SOC can do crypto operation with a fuse key. This queue is burned in hardware. You can set it using eFuses, but there's no way to extract this key. So the typical use case is you have your disk encryption key encrypted with this key and then stored on some chip. And then you ask later during boot up the CPU, please decrypt me my disk encryption key, and then with this key you can mount the root FS. Of course, if the attacker can execute code on a system, he can also ask the CPU to do the decryption of the disk key. So you have to have a verified boot that only code is run that is signed by you. If you don't have this, the game is over. A common requirement I see is that they say, the key must not be in RAM. So that's evil. And some CPUs actually support this, but there are a few things you have to keep in mind. Some mechanisms really need to have the key in plain text to do the key derivation. For example, Fscrypt, it has a master key and needs the plain text key to derive from this plain text a new subkey. And even if your encryption key is not in RAM, is in the secure memory, and it's really not readable by Linux, the file content is still always plain text in the page cache. So when the attacker can monitor your RAM, he just has to wait long enough to get all the file contents by sniffing the page cache. Of course, you can enable RAM encryption if your chip supports that, but that's a matter of your threat model. So that's why I said keep your threat model in mind. Then let's talk about crypto on system on chips. On small systems, crypto can be very slow. And even a crypto accelerator isn't always the silver bullet, because they only perform in burst mode. And so when you're really constantly firing this data into it, they are fast, but they have a huge latency, and a file system operation is usually not something for burst mode. On some systems, AES 256 is much too slow. You have to go to AES 128, and when you use Dmcrypt, consider disabling the work queues when you have a synchronous crypto method. Mostly on Intel systems, the crypto can be done synchronously and is much more faster because they don't have the overhead from the work queue. But please do your own benchmarks. So last slide. In summary, know your threat model. This is really important. You have to know what do you want to protect yourself from. There's no one-fits-all solution. Disk encryption is the last resort. Please consider encryption on the application level or on subdirectory level. And actually, the hard part is where to store the key material in a way that an attacker cannot extract it. So as I said before, here is a reading list. And thanks you for your attention, and sorry for taking too long. And if you have further questions, don't hesitate to either write David, my co-founder, and me a mail. I will also be available in the chat for questions. Thank you for your attention.